like right now if you want them, or any time. But we're going to actually use them again throughout this lecture. Is that useful to just kind of say that again? Okay. In particular, we spent a bit of time talking about the dynamics and the phase portrait of the simple pendulum, right? The point mass, a length, a single theta, gravity going down. And it had this beautiful, spooky-looking phase portrait, kind of looked like the eyeball, right? Where we know there's a fixed point at the bottom, and that it had this eyeball-looking orbits, right? Okay, this is the undamped pendulum. Would have perfectly circular orbits of constant energy. Okay, so what is this plot, right? So this plot is if I were to start a simulation of the system in a particular state and just run my simulation and plot the values of q versus q dot as it ran, then I'm going to carve out these curves. And at any point here, there's two components of that. The slope of that line is the vector field, which is x dot. And since x is q and q dot, it has two components, right? So this is the derivatives. When we set u equals to 0, it's really just this. Okay, and the point I really tried to emphasize at the end was that the way I want you to think about control is that we have a vector field everywhere, okay, that the dynamics gives us. The way that we looked specifically at the way that u entered for these second order systems, okay? U gives me the ability to change that vector field by moving it up and down. But actually, in the second order dynamics, you get to instantaneously change this component of the vector field, but not this component of the vector field. That one's just going to go with the original dynamics. So remember I said the goal is to shape the vector field to try to change the dynamics to do what you want. This dynamics is just going to oscillate forever. That's what these constant energy orbits are of my pendulum. Okay. If I added a little damping, then these orbits would eventually converge down to the downright configuration. But maybe we want to make the upright configuration stable. Right? So that's the problem of control. We already gave you one idea for control in the first lecture. And that was this idea of feedback cancellation. So if my equations of motion for this pendulum look like that, let's just say I applied the feedback law, right? So my goal is to pick the u, and I can pick it as a function of q and q dot. That's the interesting case even, is that I get to write u as a function of my current state. What if I made this choice? That was the example I showed in the first lecture where it has the effect, if I run this controller, that the system just changes to being stable in the upright. Why is that? Because if I were to put this 2 MGL here and bring it over to the other side, it would be exactly as if I had a pendulum with the equations ml squared theta double dot plus b theta dot minus mgl sine theta equals 0, which is exactly the equations of the upside down pendulum. But it's worth connecting those two ideas. So I said you can only change the vector field in the y direction. And that's all I've done with this. You have to kind of convince yourself that actually this does have the effect that it actually moves the orbits of that eyeball over to here. It changes the dynamics to be like this, right? It makes the originally stable fixed point becomes the unstable fixed point, and now it becomes stable around pi, and it's unstable around 0. And it can actually, if I have damping, it'll actually converge like this up here. And I did that just by redirecting the vector fields in the y-axis. But this is kind of a sledgehammer approach, right? This is potentially, well, for instance, MGL sine theta is going to be at most, 2 times MGL, 2 times the torque, the total, torque, the maximum torque of the pendulum. I have to have all of that torque available in order to completely reverse gravity. So in this case, this works, but control is not so interesting. It gets more interesting if I say something like, well, you have a torque limit, right? Under actuation, the B being less than full rank is one way to get it. Torque limits are another way to get interesting hard control problems. So what if I said that the magnitude of U was going to be strictly less than, I don't know, MGL, let's say, over 4. I don't know, something small. Okay, so you can't do that. Then what do you do? Well, the answer for today is you're going to write a program, and it's going to solve it for you, because that gets really hard really fast. But we can at least understand with our graphical analysis why it's hard. It's kind of fun to do it. Let me think the best way to do this. Let's just think of what the dynamics would be if I wrote this controller down and was just optimistic, but the actuator is just saturated. Okay, if I just ran with that controller, but just ran up against the torque limits, then what would happen? So maybe I'll write that as U is, we often use like the saturation function. We'll say it saturates at MGL over 4 to MGL over 4 of this other controller of 2 MGL sine theta. So I'll compute this, and then I'll just truncate it. If it's greater than MGL over 4, I'll make it MGL over 4. If it's less, I'll make it negative. If you put that dynamics back in, it's actually more, I think if I look at the overdamped case where we could draw everything super clear, it's even easier. So let me draw the overdamped case. So I'll do Q versus Q dot for the case where B is greater than MGL. So I want to say B theta dot dominates ML squared theta double dot squared overdamped regime. Where I could draw this as just a first order plot. And I'm going to draw this now as the original passive system just looks like a sine wave like this. Okay, where, remember we did this analysis, this is going this way, this is going this way, and so on, so we know this is a stable fixed point. if I applied my complete torque canceling control, if I had all the control authority in the world, then what I've done is I've changed it to be over here. I've changed it to be like an upside down pendulum. Okay, and now this becomes the stable fixed point, and this is the unstable fixed point. And remember that these limits, this top is around MGL, 2 MGL even. So if I have a limit here, some torque limit I'm not allowed to exceed, then what happens? The total effect of that torque limit is that when I'm inside the torque limit, it's all good. I get this dynamics. When I'm outside, though, I get truncated. This dynamics isn't perfectly canceled, and so I end up with this kind of weird thing that has some of the dynamics of the original pendulum, because it wasn't fully canceled, and some of the dynamics of my controller, in the case where I'm not saturated. And I get a bunch of fixed points. I'm not convinced everybody's following me on that. Do you guys kind of see that picture? That's fine, tell me that. Yeah? Okay, so did you get what the white line is? The white line is the original overdamped pendulum, which would just slowly come to rest here. The blue line is if I have all the torque, I slowly come to rest up there. Okay, now I'm asking what happens if I have the saturated controller? And when I'm in this important regime where I have enough torque, then I do get to act like this. So if I was very close to the top, then I've got enough torque and I am going to act like that other pendulum. Yes?
Sorry, I'm just wondering about the blue line. Did you say that the actuation could only shift the curve in the y direction and not in the x direction? How did you transform?
I'm glad you asked that. So, because when I said it, so these plots, the thing that I don't like about this is that this is a plot of q versus q dot, and I'm plotting vectors, right? And curves. The axes of this plot are also q and q dot, but I'm plotting something very different because this is in the first order regime. I'm plotting the overdamped b theta dot equals plus mgl sine theta equals u. So this is a different plot. It only has one variable going around, and I'm plotting the solution theta dot is a function of theta. So I'm not plotting, these are not orbits anymore. This is just, the system is only evolving along the x-axis here. There's only 1 degree of freedom in this. But since I have an extra degree of freedom on the board, I get to draw the actual magnitude of its evolution in the y-axis. So I'm glad you made me say that again, right? So it's a richer drawing. It just happens to have the same labels here, and I could totally see that being confusing. Okay, but this is the first order system, and that's a second order system plot.
So blue would be the unsaturated control.
Yes.
And then red.
Red is what? Yes, good. So red is going to act like the blue in some regime, right? Where when the blue is demand on torque is small, then you get what you asked for. When sine theta 2 mgl is less than mgl over 4, then you get what you ask for. When does that happen? That happens here, and it happens here. And then what are the dynamics when you don't get what you ask for quite? You get a constant plus the original dynamics, which is just like shifting this down, okay? And shifting this up, because it's just a constant here times that shifted curve. And the total effect is kind of weird, right? You get all these extra fixed points. It's like basically, I mean, roughly it'll say, okay, I'm gonna try to swing up, and it gets stuck here. That's one of the fixed points. It'll be over here. It could have a fixed point over here too, of like trying to go up, right? It can have a fixed point over here. It can have the actual fixed point. It's got a bunch of fixed points. Okay, it got way more complicated. And it's not a good controller. When you start here, it only gets to here. And it sits there like that, yeah?
I'm still trying to understand why U is reflected as a limit on the Q dot term instead of like acceleration. Why is it?
Yep. So the actual, it won't hit, so this line here is not quite MGL over 4. It's whenever this control, I guess it should be just a factor of 2 off that. Right. So you're right that the place where I hit the angle theta, where I hit that limit, is something we have to solve for. Yeah, it should be simple in this case. It's what, MGL over 8 or something? Yeah.
How did you find that the amplitude of the original sine wave reaches MGL?
It should be MGL over B, I guess. Yeah, MGL over B. I think when I drew it before I said B to 1, which is why I remembered MGL. Good catch. Yeah. Yes?
In this particular case, what are the, like what is Q, Q dot and U? Like as in like torque, what does that show up?
So in this plot, which is the overdamped regime, Q is still the position of the pendulum. Q dot is the velocity of the pendulum. The point is that you don't have really an acceleration. The acceleration isn't important because you're in this so overdamped regime that it looks like a first order system. So Q and Q dot are everything. U is still the torque, okay? But the plot doesn't have U explicitly. It has the closed loop dynamics of the controller under this. When I substituted in this controller for U, then the equations are just in theta and theta dot.
And is Q like position as an angle?
Yep, yep. That's an angle. So this will be 0, pi, and yes?
How would this plot change if you, for example, started the pendulum at some angle, so it started with some potential energy?
This has everything. So starting at some angle is exactly equivalent to where am I going to start on this x-axis, on the q-axis, right? So depending on where you start, you'll flow here, or you'll flow, and you can tell directly so the arrows that are drawn there are for the white line. If I did it for the other line, then it's going to flow this way, this way, this way. It's more complicated.
And how does the saturation of the motor play into that as well?
So when I look at the equations that I get, when I insert this controller, this saturated controller in, then they are no longer smooth. I get a set of equations that is smooth here, but then when I hit the discontinuity, the dynamics look like the pendulum dynamics just shifted down. So you have to, every time you hit that saturation, you have a different, possibly a kink in the plot, okay? But we can do the graphical analysis to see all of that. That's actually really good. So I mean, you'll never see this controller again. This is a dumb controller. We don't want to use this controller, but that forced us to talk through a bunch of important stuff, so that was useful, I think. The goal for today is to figure out a better controller than that, okay? And I think the high-level message is, once you have torque limits, swinging up is not as simple as feedback cancellation. That approach does not work anymore. But guess what? You can still get to the top, even if you have a little torque, right? So if you've ever been on a swing set, I guess you know that, right? But if I put a little bit of torque in at the right time, and just keep adding energy, as long as I have enough torque to overcome the damping, that's my limit, right? Then I can slowly swing up, and I can do great things with a little bit of torque, right? It just requires, what does it require? It requires longer term thinking, right? You have to think more about, you can't just say, I'm going to instantaneously go towards the fixed point. I have to think about the fact that I'm going to have to go there and then back and there, and eventually I'll get up. Okay? So the way we're going to do that is optimal control, right? Dynamic programming today. Okay, so this kind of control thinking was talking about at every Q, what would I, just trying to say, what do I want the accelerations to be at every Q? But that's short-sighted. That's saying I'm going to do instantaneously, I'm going to try to change my dynamics. If you want to do longer-term thinking, then you have to do something that you have to write down the problem in a way that thinks about a long-term evolution of the dynamics. So the way we do that in optimal control and reinforcement learning, by the way, so reinforcement learning is, I would say, is optimal control. It tends to be, a learning-based version of optimal control, right? But they're solving the same problem formulation. So instead of saying, show me your vector field and I'll tell you if it's good or not, I have to say now instead, show me an entire trajectory and I'll tell you if it's good or not. Okay? So I've got to switch to a longer term view of the world. Given a trajectory, so I'll use x dot u dot as shorthand for something like this, x of t for all t in t0 to t final. Same for u of t, yeah. Okay, the dot just means many t's. Is that okay? So if you give me a trajectory, I'm going to watch your robot act for 5 seconds. At the end of that 5 seconds, I'll tell you, was it good or not? Okay? At the end of watching a trajectory, let's say for 5 seconds, then I'm going to give you a single number saying, here's your score, right? It's like the Olympics, right? You go down the ski jump and then you get your points, right? And the goal of the optimization is going to be to try to, well, if you're a reinforcement learning person, then you try to maximize reward. And if you're a controls person, you try to minimize cost. I think controls people are, less optimistic in the world, I guess. But it's exactly the same. It's just a difference of a sign, okay? The goal of control, then, is to minimize the long-term cost. I will use the language of cost. I'm more of a controls person, I guess. So. That's the basic problem statement, is you give me a trajectory, I'm gonna calculate a score every time you run it. You can call it a cost or you can call it a reward, and I'm gonna optimize that score. Now, optimal control can be more rich than that. You can also say there's constraints. You can say optimization, constrained optimization is a powerful toolbox. some algorithms are better than others at adding constraints, but you can have constraints like, for instance, that u for all t, u of t is going to be less than some torque limit, let's say. Or another kind of useful constraint might be to say, I only want to consider trajectories where the system gets to the goal, right? At the final time, the robot gets to the goal. Say, among the trajectories that get to the goal, I want to pick the best, the policy that works best. So there's a couple really good canonical examples of optimal control that you can do without, we can think about without even understanding all the machinery for solving optimal control problems. There's some very intuitive optimal control problems. My favorite one, which I go back to a bunch, is the minimum time problem for the double integrator, okay? Okay, the double integrator is a second order dynamical system. Q double dot equals U. I know that the board's kind of dirty. Can people see that? It's okay? It's good enough? And it's interesting when U is bounded, okay? And I always want to have a mechanical intuition for these problems. So the mechanical intuition for a double integrator would just be, imagine if you had a cart, so something like this, that's unit mass. Mass equals 1. Okay, you've got some x coordinate, you're trying to get to x equals 0, and you're allowed, someone's pushing on the cart. And there's no friction. It's a really simple version of it, okay? But maybe that helps, I think, intuit what could be the optimal control approach to this. So the goal that we said is to, from any initial condition, we want to write a controller that gets to the origin as fast as possible in the minimum time. So there's a few parts of that. First, I want to think about what might the optimal policy be, because it's very intuitive. Then we'll think about how to write a cost function to get it, and by the end, we'll have an algorithm to get it. So what do you think, just intuitively, if you have this dynamical system, is the optimal policy for well, let's just even think from this initial condition. How should you get here in minimum time? Max control, right? I'm actually, when I say x equals 0, I want to be careful. I actually also want to get to x dot equals 0. So I actually want to stop at the goal. So max acceleration is the first step. And then when you get just to the right point, you got to hit the brakes, right? So you're going to jam the accelerator that way. And when you're coming in, you're going to slide into home, right? Okay, that is the optimal policy. And we're going to see it, its closed form. And then we're going to check if our algorithms get it later, okay? So let's just see if we can understand that. So I have this. Let's think about the case where let's even, I think it's interesting to start from the braking strategy, like the deceleration. So let's say I'm in this configuration and I'm hitting the brakes. So I'll say U equals -1, slamming on the brakes. And let's think about what the dynamics of that system look like. Okay, this is a differential equation I can't integrate. Q dot is just going to be Q dot of 0 minus time, because it's a -1 here. And Q of t is just going to be the Q of 0 plus t Q dot of 0 minus 1/2 t squared Let's draw the picture. This is a second order system, so I'll draw the phase portrait. It's always Q versus Q dot, but I want to draw the vectors of that optimal policy. Okay. And it turns out if you look at the solution, Q of t is Q0 plus t Q dot minus 1/2 t squared. Those solutions are going to cut parabolic arcs through state space. And we know that when you have a positive Q dot, you're going to move this way, but what you get is these nice solution curves that look like this. And actually, it's the same. If I shift Q0, I just get a shifted version of the parabola. So this is if u equals -1, I get solution trajectories that look like this. Is that part clear? These are, if I were to simulate it, hitting the brakes. Well, I shouldn't say hitting the brakes. Maybe I should say accelerating -1, because what's going to happen is wherever I am, I'm going to come to rest, and then I'm going to start going backwards. That's what's happening, right? And there's one really important set of initial conditions which gets me exactly to the goal, right? If I were to keep doing it, it would leave the goal, okay? Is that clear? Okay. If I were to do u +1, then not surprisingly, I get exactly the opposite of that. So I get trajectories that start down here, will go like this, okay? And there's one really important one that goes in like that. Okay, so the optimal strategy, which is this, it's called bang-bang control, this idea of hitting the accelerator where you use your maximum acceleration until you use your minimum acceleration. That's a bang-bang controller. The recipe, now that we understand the possible solution curves, if we only have to think about the solution curves when u is either +1 or -1, then if I'm at some initial condition here, okay, anywhere, right, I could pick any initial condition here. We said I'm going to accelerate as fast as possible, which is me going up like this, okay, until I hit this critical threshold where I'm going to decelerate and ride that into the goal. Okay? Accelerate, always, no matter where I am, if I'm here, I'm going to accelerate until I hit this, and then decelerate until I go there. Yes?
So, like, the threshold is just a red curve, it's not, like, it's a combination of Q and Q dot, not just opposition.
That's correct. The threshold is a parabola in Q and Q dot, not just position. Yeah? And it is exactly the solution of that equation when Q at some time goes through 0, 0. That's how you get that curve.
Depending on your starting position, could you do the other one?
Yep.
Where you follow a white curve and
Perfect. So if you're over here, then the thing you want to do is hit the red curve until you hit the blue, and then you slide, you go in. Exactly right. So the optimal policy, if you take that and say, let's make a map over the state space of the best action to take, there's a whole area here, including under this curve here, where the best thing to do is u equals -1. No, u equals +1. And then there's another area on the other side here where the best thing to do is u equals -1. Okay? So you understand? So I need one more color to make this work for me. The thresholds are there's a super important threshold here and threshold here. Those are the things that break up my policy. If I'm on this side, then I want to be accelerating there as fast as possible. If I'm on this side, I want to be decelerating as fast as possible. Okay? If I'm exactly on the line here, I want to be decelerating. Here, I want to be accelerating. But I'm color limited. Okay, we just did our first optimal control solution, okay, but we didn't do it, we didn't have a mechanism for finding that solution. And in fact, I haven't proven that it's optimal. It actually is, because the optimal solution is discontinuous. It's both the trajectories and the cost to go is non-smooth. It turns out it's actually a slightly harder thing to prove than you would expect, considering how simple it looks. So we need machinery that we won't get to today to prove that that is optimal, but it's optimal, trust me. Yes?
In multiple curves, you're just showing that like the threshold stays the same for any starting position. Like for any Q you would choose, like any position you start at, the threshold is going to start at the same.
So these white were just construction lines, sort of, to begin with. That's what would happen, but you'd actually don't want to take this particular white one. When you're here, you want to be on this curve, so one of the blue ones. And when you're over here, you want to be on one of the white ones. Yeah.
So like the sizing of the curves should be the same, right?
If I was a better artist, they would be identical. Yes. Perfect. Yes, they should be identical. Okay, how are we going to get that out of an algorithm? I want to kind of see if I can remember to leave that up, because we're going to compare our numerics against that policy when we're done. Okay? The way we're going to solve our optimal control problem is with the tools of dynamic programming today. We're going to use dynamic programming. Okay, and the intuition behind it is I'm actually going to, today we're going to discretize the state space and turn the optimal control problem into a graph search problem. Some of you might have seen dynamic programming first as a graph search. That's an algorithm you get in algorithms class, right? And there's a controls version of it that's completely continuous, states and time and everything. But the dynamic programming graph search you saw is exactly the dynamic programming for reinforcement learning or optimal control, and I want to make that connection. So let's think about discretizing first that state space. So what would it look like to discretize that state space? I want to make a graph on that state space. So I'm going to imagine making a little graph, or actually a pretty big graph, really, that has nodes, somehow tiled all over the state space, right? Tiling of nodes at all of my Q and Q dots. And then the edges of that graph are going to be the possible transitions for different u's, right? This would be u equals 1, u equals 0, let's say u equals -1. I could discretize more or less finely the u's also. Okay, and I can construct a graph that lives right on top of that state space. And the only way that my dynamics comes in is the way that I connect the graph. Right? It's the places that, given the equations of motion of my double integrator in this case, right, I can have arrows to some neighboring cells and not to others. That's the way that, the only way that the dynamics comes in. Okay, and more generally, we're gonna now try to think about getting to the goal as solving a shortest path problem on that graph. And if we do it right, then we're going to expect the shortest path, given the graph, is going to, it's going to look something like this, up to here and then go in. Okay? So it's really just graph search, but the topology of the graph captures the dynamics. So let's remember about dynamic programming in graph search, or if you haven't seen it, introduce dynamic programming in graph search. So my notation here, I'm going to use discrete states. Throughout the class, I will use X for continuous state, S for discrete state, to try to make that super clear. Okay? Reinforcement learning people often use S, and control people often use X. And I'm living in between the two worlds. I'm going to say, when it's discrete, S, continuous, X. Okay? Discrete actions, I'll use A when they're discrete. Okay? And then discrete dynamics, discrete time dynamics, so the way I'll write it is S at n plus 1 is some function of S at n, A of n. So I could have written a transition matrix here. If you guys think about, those of you that know, Markov decision processes and the like, but this is a perfectly equivalent way to define a function that looks like my difference equation, and it is defined only on discrete elements. Okay, so I'm going to write the state space form version of it. If you want to turn that into a transition matrix in your head, you're welcome to. Okay, but this is the dynamics way. Okay. Then I'm going to define a one-step cost, which I will call L of S A. This is going to be equivalent to an edge weight on the graph. And then I'll say my total cost is along some trajectory. Is going to be just the accumulation of those one-step costs. Okay, so this is one way to write a graph search problem. I'm going to put weights on all the edges of the graph. Okay, and I want to find a shortest path that goes from the start to the end. So more abstractly, just think of that as a small weighted graph. I picked some numbers before. Let me make sure I get them right here. 2, 2. Okay, imagine I just have a graph that this is node 1, node 2, node 3, node 4, or something like that. And if I want to take an edge this way, then I'm going to incur cost 2. An edge this way, I'm going to incur cost 14, so on and so forth. Okay? That would be exactly equivalent to having this mapped onto that picture. And they're classic graph search algorithms. There are many. People think about forward search, breadth first search, depth first search, A-star search. Dynamic programming is sort of the backwards view, okay? Where the beautiful thing about dynamic programming is you can work back, you can very efficiently solve for the shortest path from all of the initial states by working back from the goal. It's only a few equations, I'll write them down, but if that's the picture you could have in your head. And the way we do this is we take advantage of this particular structure in the way I wrote a cost function. This is an additive cost. Okay, so I chose to write my total trajectory cost as the sum of a bunch of simpler costs, which then gives it this connection to graph search and edge weights. Right? If I had the cost of going from here to here, was not just the accumulation of these individual costs, the problem is weirder and harder. Okay, the best algorithms work when we have this nice graph decomposition or an additive cost structure, because you'll be able to write down a beautiful recursion where you can kind of work through the graph directly. Questions on that? Did I say that well enough? Basic definitions? Yes?
What's the intuition behind different edge weights? Like,
So,
if it was only graph, not just states that are extremely close to each other, so the edge weights don't.
good. But for different formulations of the optimal control problem, you might prefer to take different paths, right? So, for instance, what would the edge weight be in the minimum time problem? Okay, let's give an example. What would LSA be for minimum time? In this case, which is why you're asking the question, all paths, basically the cost function is very simple. I'm going to say I'm going to incur a cost of 1 if x is not equal to x goal, and then 0 if x equals x goal. So that's that is an additive cost that has different edge weights, but the graph in the minimum time problem could just have 1 everywhere. But there's a richer version of that where I might say, I want to get to the goal, but I don't want to use too much control effort on the way there. And that's where you start writing more interesting versions of this additive cost. Yeah?
In this case, should the cost not be the time it takes to get from one node to the other node, which is not necessarily 1, depending on velocity?
Oh, good. So there is something that happens, yes, good. So there is something that happens in the discretization there. You're right. So this would be the shortest path on the graph.
Okay.
You're right. But I would actually have I would have a conversion to make time. Good call.
What are the possible examples of discrete actions? There's like up, down, or
So the minimum time problem for the double integrator, because we know that the optimal policy is bang bang, we actually don't lose anything by only considering actions that are u equals 1 and u equals -1. Maybe u equals 0 if you want to stop at the goal. Okay? So that's a case where even though the mechanical system has continuous actions, considering control actions that are only discrete is okay.
like for example in reinforcement and like grid world system.
Yes.
You have an agent and that will be like left, right, up.
Correct.
slave.
Yeah, I'll do a grid world in a second too, yeah.
So similarly, would that translate in this case more like, I'm just trying to grab it. What will be the disproportion of that?
So some problems do have a fundamentally discrete state. Up, down, left, right on a grid world is a good example of that. I think when you're doing continuous control actions, we will often, just as an approximation, change a the same way we're going to discretize the state space in order to solve the problem, we will discretize the action space and just say, I know I could do torque between 3 and negative 3. I'm going to just say, I'm going to approximate that with 3, 2.9, 2.8, 2.7. And if I can solve that problem more efficiently, then it's an approximation to the original problem. Yeah?
Instead of discretizing, could you like approximate it as a polynomial and just choose the coefficients?
We're going to do better things like this soon, yeah. Polynomials in particular can work out, yeah. But typically not in time. That's a little bit, well, so, okay. Yeah, there's like 4 answers to that question, but yes is yes to all of them, yeah. So there's a trajectory case where we'll parameterize trajectories and optimize over polynomial trajectories. Also polynomials over state is going to work out okay too, yeah. Yes?
You can't always take an action at every time, like if you have some, let's say copper, when it's in the air, it can't do anything.
Ah, okay, but the dynamics will still evolve. So that's an interesting case. So if I had a hopper and I was up in the air and I couldn't change or let's say my actions were effectively useless in the air, I might have places where I'm on the ground where I have, lots of different, this might be, in the ground where you have lots of control authority. And in the air, you might just have this. And when you're in that part of the graph, the dynamics is telling you where you go. You don't have any choice, right? But if you can solve the graph search problem through, to make the right decisions back here so that when you go here, you get to the right place, that's exactly the game we're playing.
So we were looking at like time dynamics as a function of like an action and a state. Would that only be relevant when an action was just taken?
Yes, this is a one-step action. Yeah, this is the one step. Good. Okay, the key idea in dynamic programming is the notion of a cost to go function. Also known as the value function. And we will use it heavily. There are many cost to go functions, okay? The optimal cost to go function would be if I'm taking optimal control actions, right? And I'm in some initial state, how much cost do I expect to achieve as I get to the goal? Right, that would be the optimal cost to go function. But for any controller, you can ask, what is the cost I expect to accrue from this controller, right? And the optimal cost to go function says if I'm in some initial condition state Si, it would be the min over a long-term action. So all of my actions into the future, I've taken the optimal actions. N is 0 to big N, whatever big N is, it could be infinity, of the transition costs, the edge costs, subject to S0 equals Si, and then my dynamics. I'm sure why the screen's going crazy there. But. Okay, this is saying if I started this state and I do the best, I can take the best possible action in every state, how much total cost am I going to obtain? Right, that is the cost to go function. In RL, it's typically called the value function. In controls too, it's called the value function. Okay, and it's a super key idea, and it's the key to dynamic programming. The reason it's so useful is because you can solve for it recursively. By realizing that the best thing I can do and the best cost to go I can possibly get in one state, I can also say, by the way, this star is my notation for optimal.